Okay, so what did I just do? There we go. We're on to chapter 5, which is about memory, and specifically it's about system memory, although we talk about memory in general and talk about memory that the other memory that we have a little bit in this chapter, that being memory that comes with our CPU. So it's still not working. Dang nabbit. Why not? Okay, so the goal of today is to get through basically half of the new information, and then you're going to do some reading and a little exercise as well. But we're going to try to introduce and talk about memory. And why is this not working? Why? Let me recalibrate. See if that helps me at all. Nope, I shouldn't have done that. Nope, shouldn't have done that either. It is not receiving right or something. Gonna be way off. It's close. For some reason, not getting up there. So we have two different kinds of RAM on our motherboard. Okay, we have static RAM, SRAM, and we have dynamic RAM or DRAM. Okay, both those exist. It shouldn't really say on our motherboard. It should say RAM in the system, because one of them is not really on the motherboard. Static RAM is RAM that it's written to, and the information that's on the RAM stays there. It's static. That's what the definition of static means, right? If I put something someplace and it doesn't move, it's a static. Okay? So RAM that doesn't have to be written is static RAM. I almost tried to use my eraser there. That wasn't going to work. And dynamic RAM is RAM that changes or is really, really volatile, in that in both cases I have to have power to maintain it. Dynamic RAM is refreshed continually. It's continually rewritten so that the information stays there. The memory controller on the motherboard is responsible for rewriting it, refreshing it. And the information, and it says DIMMs or RIMs. RIMs are old. It's really in DIMMs or dynamic inline memory modules. And we're going to show you what these look like today. But of these two, static it doesn't have to be rewritten, so it's faster, but it's also more expensive. And because dynamic has to be rewritten all the time, that makes it slower, but we use it because it's cheaper. Okay? Now, we have two places that the motherboard, with the CPU stores information that's primary storage, right? It's all memory, but those two places are what? Name one of them. What?
Would you say it was
Two places on our computer that we have memory. Can you think of one of the two?
the RAM socket?
Okay, we've got the RAM socket. So we have the system RAM that plugs into the motherboard. That's one of the RAMs that we have. And what's the other RAM we have? CPU cache. Okay, we have both those two places. Now, just by this alone, if we use both those, one of them's in one of them's in the other, which one would you assume is probably the faster, more expensive one? Cache on the CPU or system RAM? It's cache. Okay, cache is really fast and it's really expensive. That's why when we talk about, oh, this one's got tons of cache is 2 meg. Whereas when we say we have tons of RAM, we're talking about 16 or 32 gigabytes, because dynamic RAM is so much cheaper. Okay, so CPU cache is static, it's faster and expensive, and the system RAM is dynamic, it's slower and cheaper. Okay, and that's what this next slide basically says. Okay, our main memory, our DRAM, our system memory needs constant refreshing. Don't know what's going on with OBS Studio today. I don't know if the recording's happening or not. It's slower because of that fact that it has to keep being refreshed. Okay, and it's physically housed on DIMMs anymore, which are our memory modules. Whereas cache memory is static RAM. It doesn't need to be refreshed. It's very fast, but it's also expensive, and it's housed on the CPU itself. Okay. So this is the only slide we're going to talk about cache, because really cache is something that we talked about last chapter. It's all static RAM, and it's all with the CPU, right? We can't just go and buy and insert cache. It comes on the die when we buy the CPU. And that's one of the primary memories that a CPU talks to. The other one is system memory, which is what really this chapter is all about. It's about the kind of memory that we can buy and put in our motherboard. So we talk about RAM, we're talking about that whatever kind of RAM that goes with that specific motherboard, and we're back to form factors. And different motherboards have different form factors to support different kinds of RAM, and they are therefore supported by different kinds of CPUs as well. So when we go to any one of our motherboards, we know that we see this little section down here on memory, and now this chapter is really more about what this is, okay? When we talked about motherboards for this specific one, we could see that it's got 4 slots, and it takes all these different kinds of DDR4 RAM. It takes up to 64 gig, but now we're going to learn more about what goes in there. Just like with a CPU, there's more to know than just the speed. There's the cache and the number of processors, the number of threads, all go together to determine how fast it is. Really, there's more than just this number when it comes to memory. But that's the number that everybody looks like. Just as CPUs, there's only really one number that many people look at as well. So we're going to learn more about what this all entails in the different kinds of memories. So memory evolved from way back to the first RAM that I ever used on a PC, which was a SIM, which was a single inline memory module, up to DIMMs of today. And specifically, the ones that we're going to talk about is called SDRAM, or Synchronous Dynamic Random Access Memory. Okay, everything that's in production today is a version of SDRAM, and this is the oldest and first version of SDRAM. I keep seeing it connect and disconnect. I don't know whether it's working or not. I guess I'll look later. And the reason I want to go back here to the original version of SDRAM is to help you understand the naming convention and where the naming convention came from. Okay, so the first versions of SDRAM really were here when I got to Trail. That's the first ones, and they looked like this. They had 2 notches in there, and all the versions of RAM were the same physical size, but this notch helped determine what the form factor of it was. And back when SDRAM first came out, it went 66, then 100, then 133 megahertz. Okay, and we know now it goes up to 4,000 megahertz is the speed of RAM. So the original SDRAM, these are the speeds. And the only reason I'm bringing this up is that you understand where the naming convention started. So the fastest SDRAM, when we used SDRAM, was 133 megahertz. And then we got what was called DDR RAM. And DDR in the beginning stood for double data rate. And the first one came out at 266, that's a 6, megahertz. And so it was double of that. And that's why it was called DDR RAM. It was twice the speed of, and by the way, it's still SDRAM, it's DDR SDRAM. So when DDR came out, it stood for double data rate, still does, but it was double of SDRAM at one point in time ever. Because this evolved all the way up to 400 megahertz when it was called DDR. So it was double right there. It's not double anymore, now it's triple. Okay, so when it first came out, that's where the name came from. But it doesn't really mean that. I mean, it technically means double data rate, but it's really not double of anything anymore. Okay, so it came out of that when it was DDR, and originally it was called DDR. And then we got DDR2, DDR3, and DDR4, which are really the second generation, the third generation, and the fourth generation of DDR, but it's not really double anymore. Does that make sense? It's just kind of a weird term that we continue to use DDR 2, 3, and 4 when it's not double, it's 10 times faster, right? So when we went to DDR, though, we went to 1 notch instead of 2, and my pen's not working again. Hello. Hello. Okay, we'll pretend there's a little notch there. So we had one notch when we went to DDR, and that was one of the first things that we noticed between when we went to from SDRAM to DDR. But then as we moved through the different versions of DDR, the notch just kind of migrated around so that you couldn't physically shove one piece of DDR into the spot of a different kind of DDR. So DDR, the notch was here, DDR2, the notch was there, DDR3, the notch is here, DDR4 actually goes back over here, which is closer to where it was in the beginning. Physically, it continued to be, and my pen's working again, the same width, but that's it on the similarities, okay? If you look real closely, there's way more connections down here on DDR4 than existed with DDR. They just got thinner and thinner. These little gold connectors got thinner and thinner. So as we went through, these physically wouldn't fit anymore. And I have had people try really hard to get the wrong one in, okay? I just had a friend of the family who was building a whole system, and it was a DDR4 motherboard, and he got a really good deal on DDR3 RAM, and he's leaning as hard as he can on that motherboard trying to get that sucker to click in there. And I was like, hey Will, hold on a second, let me look at something. And I pick it up and I'm like, Will, this is DDR3 and that's DDR4 and you're not going to ever get it in there. He's like, but it was such a good deal. And okay, doesn't matter. I know that I've told you guys when we take a memory in and out that you have to kind of lean on it to get it snap in there, but you always have to look to make sure the notch lines up first. Even if you have DDR3 for a DDR3 memory motherboard, if you flip it the other way, it's not going to go in. And people have done that before too, where the notch isn't lined up with the physical notch inside the motherboard itself. So it's, again, no matter how hard you push, you're not going to get it to go in. So this picture is really just to show you the physical aspects of the evolution of memory. That the notches are different places. We've got way more connections here. Physically, it's the same size. It looks like it would go in, but that doesn't mean it will, okay? And in all these, okay, all of them except for one, but we'll talk about that in a little bit. But all of these pretty much have, let me go a different color. 1, 2, 3, 4, 5, 6, 7, 8 modules of memory on them. Why do they have 8? Okay, don't look at this one because that's something else. But all of them have pretty much 8. Why 8? How many bits are there in a byte? What? 8. There's 8 bits in a byte. And whenever stuff is written to memory, the packet is always in a byte. It's always a byte. And so when I get a byte package written to the motherboard, or written to the memory module, erase. Okay, I'll do it the hard way. No, I won't do it the hard way. Control L. There we go. It writes that byte by putting 1 bit here, 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 1 bit here. That's how it writes a byte. Okay, so it stripes it across there, and memory is held in kind of a huge table on these modules in columns and rows. And every time it goes around and writes data, it takes so long to do, and it always writes it in that column and row. So that's why there's always 8 in line, and this one, you see that this is a bigger module, so it's still 8, but it's got 2 modules here. This one is something else, and we'll talk about that later. This was a bad picture to go in with these because it blows the whole 8 thing, but you'll learn why there's 9 sometimes. Okay, so they look the same. They write the data in these columns and rows as the information goes around the motherboard and goes back and forth from the CPU. And the CPU is the only thing writing in memory, right? The motherboard has a memory controller that moves data from the CPU to the memory, back to the CPU, and it will move stuff through from the hard drive, from the memory controller to the memory and back and forth, okay? So it's moving really, really fast, and it's going back and forth. And it could be any of these generations, but it's totally determined by the motherboard, and the motherboard firmware determines which of those speeds, right? Because when you looked at your motherboards although this is a terrible picture of this, because this one takes almost everything that's DDR4, but many of them only took 2100, 2133, 2400, maybe it only took through 3000, didn't take every one, and that's because the motherboard is programmed to take only certain speeds of RAM. So you have to match those speeds up along with the form factor there. Okay, this is in the reading that you have, but it's really to show the evolution of SDRAM through DDR, through DDR2, DDR3, and DDR4, and it doesn't go all the way. This only goes to 2066. But as we move to new evolutions of it, DDR went all the way up to 400, and then when we moved to DDR2, it started at 667 megahertz, and it went to 800, and then DDR3 really started at 800 and went all the way to 1600, and then we came out with DDR. So that's part of the reason we got a new generation, is because it was getting faster, and those CPUs that went with the motherboard that did DDR3 couldn't handle DDR4 memory, so we had to come up with a whole new form factor for those things to match up together. So I'm not going to ask you all those numbers or anything, but it's just to show you kind of the evolution of speeds that went through there as well, and we're going to talk about that latency number over there in just a second as well. But that's why they're arranged the way they are. Also physically, you need to know that these modules are, I gotta grab a pen there, don't I? There we go. Are called DIMMs if they're for desktop memory. If they're for laptops, they're called SODIMMs. Okay, so SODIMM is for a laptop. They're smaller, about half the size, and DIMMs are for desktops. They're defined almost exactly the same way. We can see the same speeds, the same requirement kind of specifications and stuff. But when we do our projects, all of our projects are going to be with DIMMs, because they're all going to be for the motherboards that you guys presented back in chapter 4 in the beginning, right? So it's, again, a building approach. So these are, you can see, these are SDRAM, and these are DDR, but idea is the same, that they're about roughly half the size of DIMMs. So if you see SODIMM, you know you're talking laptops, okay? They're small form factor DIMMs. So when we talk about RAM, just like with CPU, we talked about things in gigahertz. In RAM, we talk about speed in megahertz, okay? So you're gonna, boy, that's really frustrating. We're gonna talk about that speed in megahertz, but there's more than just that helps determine relative speed of one stick of RAM versus another. Okay, just like with CPUs, you couldn't say, oh, this one's 3.2 gigahertz and this one's 4 gigahertz. 4 is faster. 4 is not faster than 3.2 because we have to take into account the cache, and we had to take into account the number of cores. Well, the same speed of RAM could be totally different or slightly different. So when we look at them, we've got other things besides just that core speed. So when we look at DDR4 2400, that's saying it's 2400 megahertz RAM. What is yours doing? It just keeps restarting. Comparing disk errors. It might take over an hour to complete. How long has it been going on? Did it just happen today when you turned it on?
Yeah, just right now. It just completely blacked out. And then it started the reboot, and then it just completely shut down.
And then it's doing a hard drive check. Okay, well, we might swap your hard drive out here in a little bit. I've got one already image that we can pop in there if it's not going to play. So when we look at memory, there's desktop memory, there's laptop memory, and there's server memory. Then we've got other things that impact our speed, one of which is timing. Okay, when I talked about the fact that it writes across those memory modules, I'm not going to draw 8 of them, in rows and columns, that timing is what is right here, where it says timing 16, 16, 16, 36. And of those 4 numbers, one of them, the first one, is called the CAS latency, or the column latency. In other words, that's how many trips around the motherboard it takes to fill up a column of data. Okay? So it takes 16 trips around the motherboard. Now, it's going at 2,400 revolutions, 2,400 million revolutions per second. okay? And so if you wanted to divide 1 second by 2,400 million and then multiply that by 16, you'd find out how many nanoseconds it actually took to write that data, okay? Now, why is that important? Because if I'm looking at 2 sticks of RAM, both that have the same speed, then I would want this number right here, this latency number, to be higher or lower. That's a question. If that's the number of trips around the motherboard it takes to write the data, would I want that to be a higher or lower number? Lower, okay? Latency is how long it takes for it to complete a cycle of writing to memory, okay? So if I'm comparing 2 sticks of the same megahertz, the next thing I can look at is the latency, and the one with the lower number writes faster. And that's one of those things, that's the timing, that says, okay, what impacts the speed of my RAM other than just that megahertz? And that's number one, okay, is what kind of timing does it have? If one of them has 15 and one of them has 16, the one that only takes 15 trips around the motherboard to write it is faster than the one that takes 16. And as we compare and look at ones, and you'll get a test question that says, which one of these sticks of RAM is faster? They're both going to be the exact same megahertz. The question, or they could be the exact same megahertz. The question then falls down to timing. Which one has a lower latency on its timing? Means that one's faster. And that's one of those things that a layman doesn't know. They just look at that number, right? DDR4 2400, they're all the same. No, they're not. Okay, so that latency is one of the things that I can look at. The next one is architecture. What kind of architecture does it have? And in this one specifically, we're talking about how many channels does it support, okay? Dual channel, and you're going to read an article about dual channel architecture, basically means that it could write on the way on an up and a down at the same time as it's going by the RAM. So basically it gets twice as much done on a trip by than one that doesn't support dual channel. And there's some things that, man, I'm having mouse issues. No, I can't. What's going on? Okay, what, you can do that, but you can't move. Is my battery almost dead? Okay, well, I'm just going to type and see what happens. Motherboard, nope, I'm only getting... What in the world? I'm going to my other thing. Maybe I need batteries on there or something, I don't know. It's not that old that it should need. Oh, that's a terrible picture. I didn't work at all. Actually, let me do this. I can actually bring up a motherboard and see if I can find one. I'm not even staying connected. It's really weird. Okay, this one's good enough. Okay, so I've got this motherboard. Let me see if I can get a good picture of the motherboard. Okay, so there's my picture of my motherboard, and there is my RAM. Okay, so as I look at that RAM, I see two distinct colors in the RAM as I look at it, and I can pull up the specs on the motherboard and see what kind of, and by the way, both the memory and the motherboard, like everything else, has to support, let's see if I can do this. Specifications down here and go down to my memory. Okay, so right there it says it supports dual channel memory on the motherboard. The memory also has to support dual channel memory, in order for that to work. But I also have to install it right. So when I look at a motherboard like this, the reason I have two colors, the reason I have gray and black, is because in order for that dual channel to work, I have to install it right. If I get two sticks of 8 gig RAM and I put them right here next to each other, I've negated the dual channel because they have to go in pairs, hence the dual. Okay, so I would have to, if I got two sticks of identical 8 gig of RAM, I'd have to put them in 2 gray or 2 black in order for dual channel to work. So I have to get the right architecture of RAM and the right form factor for RAM to get it to do that in my computer. If I got different sizes, it doesn't work. So if I got a 2 and a 4, I just got 6 gig of RAM. But if I did a 4 and a 4 in the 2 grays or the 2 blacks and they matched, then it's going to do dual channel, and that 8 gig RAM is going to be faster than if I just shoved an 8 gig stick right here. Okay, so it's better if I utilize that dual channel. Okay, now if I only have 2 slots and I can only afford 8 gig, I may actually buy an 8 gig stick, saying that later I'm going to get another 8 gig stick, so that I can use dual channel. But I have to put them in pairs that match on my motherboard when I do that. And let's see, my arrows work? My arrows don't work. Let me go try a new battery and see if that brings me back to life. Here we go. I'm just dying here. So my timing is this latency timing, or the first number there that I could use compare. The architecture is what kind of kit does it do dual channel? Does it do tri-channel? Does it do quad channel architecture? And quad is usually when we're getting a lot of memory into a server, and tri-channel is kind of old. There was a point where we were doing tri-channel and it's gone away. Mostly it's dual channel and quad channel memory that we're looking at now. And then type goes on to whether it's server memory or desktop memory, and we're going to talk about that and what we can add with server memory that impacts our speed as well. So when we look at memory, really we're looking at speeds in megahertz. We don't really do the nanoseconds, although you can do the math and figure it out. But generally when we're looking at it, that's basically saying we're going to take that speed in megahertz, we're going to divide it by the latency, and we're going to figure out how many nanoseconds it takes to write, which means nanoseconds should be high or low. Low. Nanoseconds we want it to be low to be fast. Megahertz we want to be high to be fast. And PC rating, really, it's kind of I'm going to look at this. Maybe I'm not, because I'm going to keep hitting the left arrow there. And when I look at this, every stick of 2400 has a PC rating of PC4 19200. It's just another way of saying the speed of the RAM. Okay, so to say this makes an impact, well, it's the same as saying this, because there's no different numbers for the same speed of RAM. So I don't really like comparing PC numbers. Higher is better, just like megahertz higher is better. How much memory is installed in the system does not make the memory faster. Okay, if I put in 2 gig of 3200 PC3 and 8 gig of 3200 PC3, the memory still go on the same speed, but the overall system could be faster if we put in more memory. Okay, to a point. If I put in 128 gig of RAM in a system that I'm doing Microsoft Word on versus 8 gig of RAM, I'm going to see no difference in speed. Okay, the memory technology being used, that's where we're talking about dual channel and tri-channel and quad channel RAM, is going to impact our speed. The CAS latency or CAS or CL is going to, the lower number is better. And then finally, this one we're going to talk about really next class, because this is whether it does error checking, and that really applies to servers. And so what kind what kind of error checking it does impacts the memory speed. And like I said, we're going to read and talk about that next class. So this is their chart. More RAM does not mean faster RAM. It means a faster PC to a limit. The technology, DDR is all that exists anymore. These things don't even exist. Lower response time in nanoseconds, and that's a 7.5 and that's a 70. So means more. Faster rated speed means more. This is obviously an old chart. Higher PC rating means more. And then if it has a lower CL is better, and if it doesn't check for errors, and you're going to learn why, it makes it faster as well. So there's a bunch of things that go into speed of RAM. Now, what you're going to do the rest of the day today is I broke down over Christmas the whole RAM book into more finite parts, okay? So in the textbook, you're going to go and just read these first 4 sections and pick up the stash while you're reading it, because as soon as you pick up the stash and read those sections, you'll see this little set of questions come up. It's 5 questions over the reading, okay? So as you read through there, so it came back up fine. That's weird. As you go through the reading, pick up the stash, take notes, and then you should be able to answer these journal questions, hopefully by the end of the class today. We're going to continue next class with the other sections of RAM. I just don't want to do too much info at one time. So you're going to read over kind of the things that we just talked about today. It's obviously more in depth than I just went over it, so you have time to read and take notes. Does anybody have any questions before? Okay, so that's your assignment for the rest of the day today. And like I said, you will see those things, I don't have it on the right section, show up down here. As soon as you've read through those first 4 sections of the memory book through here, through architecture, you will see the assignment show up there, and it's just a journal with 5 questions, and you're going to answer those questions.